My name is Hugh Crowl, and I'm an astronomy faculty member here at Bennington. When I was young, I didn't want to be an astronomer. Not because space and planets and things didn't fascinate me. I was actually obsessed with them, actually. But what I wanted to be was an astronaut. Just observing these things from Earth hardly seemed enough. I wanted to go to these places. I wanted to see Mars and Jupiter and Saturn. Really sort of scanning on the surface. I wanted to see and know planets outside our solar system. We didn't know yet that those planets existed when I was here. We do now. But that didn't stop me from wanting to go and find out. I don't think I'm at all unique in this design. I think that this spirit of exploration is prominent among all of us. Dr. Laurie Leshin has pushed us closer to this goal of exploring our universe. She's a planetary scientist who in June will become president of Worcester Polytechnic Institute. She has been at the fore of this spirit of exploration. While she hasn't personally been to Mars, okay. As leader of NASA, she sent unmanned missions there. She worked to send unmanned vehicles there and develop a roadmap for the future of human exploration. She paved the way for astronauts to actually go to the places that we look at. Look out at the sky and see. Prior to being at NASA, Dr. Leshin was a professor of geological sciences at Arizona State. Of course, she met Bennington's president. In the true spirit of Bennington, we're not only going to hear from Dr. Leshin today, we're going to hear from Susie Ibarra. Susie is an innovative composer, improviser, percussionist. As should be apparent from her collaboration with planetary scientists today, Susie is interested in interdisciplinary art and education. Her recent work blends traditions and crosses rhythms and tunings from around the world. Some of her recent work has been inspired by the first explorations of space. And with that, let's go exploring.
special day. I'm so honored to be here, both to be here for President Silver, and also to get to do this amazing new collaboration for me. I think it's so fitting that inaugurations are about new beginnings and new promise and new ideas and thinking big. And for me personally, it's been a great opportunity to expand my own way of thinking about my work in the universe by doing so in collaboration with such wonderful musical talent here. So I'm really thrilled. And we're here to ask what I think is the biggest of questions that scientists can ask. And in fact, it's got a lot of implications for all other aspects of what it means to be human, what it means to be living on our planet. Are we alone? And this is actually a question that we scientists get to ask and are coming close to being able to answer. And I want to share with you today a bit about how we think about this question and how we go about trying to answer it and where we are in that great, great quest. Now, doing so, we get to look at amazing images like the ones we just saw, which are from my favorite telescope, the Hubble Space Telescope. Incredible images of our universe, things that can both inspire us, our scientific curiosity, but also just inspire our imagination to imagine what's possible. So we'll look at a little bit more of that, and they're very fitting for this first section of the talk, which when I was collaborating with Susie and bringing this together, I said, this is the part when we blow their minds. So this would be the first part. So in order to think about, are we alone in the universe, and get some context on what does it mean to be in the living universe, we need to understand both the time and the space that we're thinking about. So we'll start by thinking about the time. So, any Cosmos fans out there may have seen a rerun of this recently that Neil deGrasse Tyson is doing. This is the cosmic calendar. So one of the hardest things to explain to students or to anyone about space and time is the vastness of both that we deal with in our business. So to help with the time aspect, let's do a thought experiment which says, let's compress the entire 13.7 billion year history of the universe, as Carl Sagan would say, 13.7 billion year history of the universe into a single calendar year. So Big Bang, January 1st, right after midnight. Now this moment right here today is at midnight on December 31st. So got it with me? So that whole time is compressed into a single year. And so then that can give us some perspective on when different important things happen, like, and this is a quiz, so, okay, we're in school. When did the Earth form? It's a date between January 1st and December 31st. Anybody got an idea?
December 30th.
Okay. Anybody else?
August 1st.
Good, you guys were rapid at it. So there it is. So our sun and system of planets, which form together, which we'll talk about in a second, happened towards the end of August in our cosmic calendar. So lots of stars lived and died before our star, the sun, was born, and the planets with it. That's important because all the stuff that we're made of, most all of the stuff that our planet is made of, was actually formed inside those earlier generations of stars, which were really just started out as hydrogen and helium and smashed those things together and made heavier and heavier elements. Then exploded their star stuff out into space. That stuff then formed the next generation of stars and the next. And so the carbons and nitrogens and the iron in the core of the Earth all formed within earlier generations of stars. So that's where the Earth formed. Now, dinosaurs, long time ago, right? Dinosaurs, ancient history, right? So when did dinosaurs roam the Earth? So range of dates.
December.
November, December, December 21st to 28th. So the extinction of the dinosaurs. Well, first of all, they lived for a long time. It's 4 days in this calendar. 5 days. It's a long time. But way longer than things have been around. They lived a really, really long time. But we think of the dinosaur extinction as being a really, really, really long time ago. December 28th. Humans, earliest ancestors, humans, came on the scene at 10:30 p.m. on December 31st. And that's the early humans, right? All of history, every history class that is taught at this institution, our students take, literally takes place in the last 10 seconds of December 31st. The second on this cosmic calendar is about 5 or 6 human lives. So it is literally 5,000 years, those last 10 seconds. All of recorded history, all of the history that we study in history books. So this is the kind of time frame we're dealing with when we think about the history of the universe. So we're starting to get to the whole mind-blowing thing yet? Yeah. Okay, good. So that's time. Long periods of time that we're dealing with in space for things to happen. Now let's talk about space itself. So there it is, my favorite telescope, the Hubble. And this is one of my favorite images. This is called the Hubble Deep Field. So this is to get at the space dimension, how much stuff is out there in the universe. So this is a beautiful image that Hubble took. Hubble took this image by, well, let me back up and say, when you look up, when it's not cloudy, at night in the sky, and you see lots of stars, and here it's nice and dark, so you can do that. Almost all of those stars are stars in our own galaxy, the Milky Way. The Milky Way galaxy is a great galaxy. It's a couple 100 billion stars in it, big galaxy. We're looking at those stars at night. And what Hubble did here was it said, I'm going to look at a place in the sky where you can't see the stars, where it's just dark. And I'm going to take a really long exposure, so I'm going to stare for many hours and take this picture. So this is a picture of a very dark part of the sky. And lo and behold, there's a ton of stuff in this picture, right? There's thousands and thousands of these points of light. These points of light are, in fact, not stars, but galaxies. So each one of these little points is a galaxy. You can start to see if you look close. There's a nice swirly one there, there's a swirly one down there. Each one of these galaxies is a lot like our own, has hundreds of billions of stars in it. Most of them are like our sun, because our sun is a pretty average star. So you can ask, there's a few thousand of those galaxies, each with hundreds of billions of stars in it in this picture. How big of a piece of the sky is this picture? This picture is a piece of the sky about the size of the eye of a needle. Good. Appropriate reaction, I like it. Okay, so tiny piece of the sky, thousands and thousands of galaxies, each with hundreds of billions of stars in them. Oh my gosh, we can start to feel pretty small, right? For the last 10 seconds on December 31st, we're one star in a giant galaxy that's one of billions of galaxies, each with billions of stars in them. We can start to feel kind of apart from the universe, like we're different or we maybe don't belong. But in fact, the more we study, the more we try to understand what's happening in the universe, the more we see we're really a part of it. That all of the things that we see and deal with in our nearby space are things that are kind of a natural consequence of the things that are going on all over the universe. So here's an example. So we can look at not just other galaxies, but here within our own, we can see places where stars are being born. We can watch this process happening. New stars and new solar systems being born. This is in the Orion Nebula. And when we do that, we can test our ideas about how solar systems form. So solar system is a star in the middle of the planets going around, right, like ours. We only, until very recently, had one example of a solar system to study, a star with planets. That was ours. And when we observe our solar system, what do we see? We see a big star in the center, planets, 8 or 9 of them. We don't have to have a big debate about Pluto here. We can do that later. All going around the star, basically a flat plane, basically all going around in the same direction. So it's kind of like this big flat thing going around. And so the idea came to be that, in fact, solar systems were formed when you formed a star. You had this little spinning cloud of gas and dust that starts to collapse in on itself for some reason that maybe we don't totally understand. But most of the stuff goes to the center and makes the star. And because it's spinning, as most of the stuff goes to the center, it spins faster and faster, just like an ice skater pulling in her arms. But because it's spinning, it also, some of the stuff flattens out into a disk. And as that disk cools down, dust particles form, and those smash together, and ultimately make planets. So that's kind of our general idea about how solar systems form. But we've never observed another solar system. We've never seen one of these disks. Our disk is long gone, except for our planets. Until Hubble showed us these stellar nurseries where these disks were forming. And so here's one, looking at one of these stellar nurseries, these disks here against a white backdrop here. Here's another one. These are actually about the size of our solar system. So we're now watching the theories that we had about how solar systems came into being in action in space. And the good news about this is that when you make a star, you ought to make planets a lot of the time. this is a good thing if you want to look for life. So understanding that, in fact, making planets might just be a natural consequence of the same process that makes those billions and billions of stars in those billions of galaxies. And so maybe, just maybe, this is a natural consequence of the process of forming the stars that we see. So maybe we ought to be optimistic about finding lots of Earths out there. And so here's our own wonderful planet. So recently taken photo of our beautiful Earth, which turns out to be a lovely place to live, don't you think? It has lots of characteristics that make it really wonderful place to inhabit, and we'll talk about those in a minute and how those guide us towards the way that we search for life elsewhere. So what I'm going to do now, we're going to show you another little series of images and animations. It's a bit about life on Earth. We'll show you some different extremes from the beautiful colored algae microscopic organisms living in Yellowstone, or the little blind shrimp at the bottom of the sea in black smokers. You're going to see a beautiful animation of the Earth turning with different colors, and those are life on our planet, both on land and in the sea. So that's the living, breathing Earth. And then you'll see, we'll end with a couple of animations of human impacts on our world. Life on Earth teaches us so much about how to think about how to look for life elsewhere. We can have a discussion at the end if you like about what it may or may not teach us. Maybe we need to be thinking more broadly, but life on Earth is so diverse and so incredible that in fact it teaches us so many things. So we learn how to look for life elsewhere by looking at ourselves, at the history of life on our own planet. If you remember ourselves humans, we're only there for that last 10 seconds of New Year's Eve, right? And so, in fact, what we need to understand is the whole history of life on our planet, and you've got to see some really awesome and strange life on our planet, those different colors at Grand Pacific Springs, Yellowstone, or did you notice the little albino shrimp on the black smoker living at the bottom of the ocean without any sunlight, so that there's different kinds of food that life can use to get its energy. You don't have to live near the surface, you can live in the deepest, darkest places. So we learn about the kinds of environments that can support life on Earth. We also learn about the history and how far back life goes. And to geologists like me, this is great, because this is all about going and studying rocks in the field. And when you go back in time on Earth by looking at something actually as far back as we can go, because we can't go all the way back on Earth because tectonics and things changing around the surface of the Earth, but we can go back to rocks that are 3.5 billion years old. That is almost as far back as the end of August, but maybe that's more like the middle of September, they say, in terms of geologic history. And when we look in those very oldest of rocks, we find things like this. We find fossils. So this is a microscopic set of pictures from a 3.5 billion year old rock or so. That's right. And then this is a scientist's conception, if you will, of the very small, but still unmistakably a living organism billions of years ago. Turns out that life got started on our planet pretty much as soon as it could. As soon as it stopped being kind of nasty with all the things impacting us all the time, and that things settled down, the oldest rocks that we can find seem to have evidence that there were living things. Rocks even older than this rock seem to show evidence that things were alive as far back as perhaps even 4 billion years ago. Incredible. So life got started really quick. That's interesting. It also stayed really simple, not so much different from this or like the blue-green algae in the pool, for a very long time, billions and billions of years. It was complex life, not to mention intelligent life, which only came along at the very end, that turns out to be the harder thing. So maybe as we're looking for life elsewhere, if we're looking for life on another planet, we shouldn't be looking for little green men, but little green algae. So we learn a lot from studying life on our planet, and when we do that, here's kind of the checklist, the recipe. Those are the things that we need to go look for places that might bring these ingredients together. It's a little bit of a simplistic view, but not overly so. One is liquid water. Everywhere we find life on Earth, there is associated liquid water. You need some kind of a liquid medium to do all the chemistry of life, and liquid water works really well. You need the raw materials. You need the stuff that life is made of, the carbons and the hydrogens and the nitrogens and the phosphorus and all that stuff that comes together to do that complex chemistry that is life. So you've got to have the raw materials. And then you need food. So that's the energy source. For us, it might be a turkey sandwich like I had for lunch. For those things living at the bottom of the ocean, the black smokers, some of them actually live on chemical reactions in the rocks. They can actually derive energy from doing from changing the chemical compositions of rocks. And so there's a lot of different ways to eat your lunch if you're life out there, and that's a good thing. So volcanic, thermal heat can drive things that simple life can live on. All sorts of possibilities are there, and that kind of opens up the blinders in terms of the kinds of environments where we might find life. But really, when we start to think about, okay, where are we going to go and look for life, this is a good list to use. And it turns out when we say where in our solar system, just in our little space neighborhood, are the best places to go, the one that always seems to pop out and come to the front is Mars here. Beautiful red planet, the next planet out from the sun. And in fact, Mars is a place that we've spent a lot of effort exploring this question about life elsewhere, and it remains probably the most interesting place to do that because it's accessible and because it seems to have had the ingredients. The question is, do we that's what we're trying to figure out. So here's Mars. It's a wonderful place to explore if you're a geologist. It has giant volcanoes over here. It has a huge canyon system that would go all the way from LA to Bennington here. So all the way across the country, it's a huge canyon system. It has an atmosphere. It's a thin atmosphere, but it's an atmosphere nonetheless. And it has its spin axis is tilted like the Earth, so it has seasons. It's got summer and winter, and it's got polar caps that grow and shrink in that time. But all those things are a bit secondary to this question about life. What's most interesting from that perspective, and it's a little bit hard to see here, but you can kind of see up here, one of these big channels, it has thousands and thousands of dried up riverbeds on the surface. So we can look and we see all over the planet places where water, we think, must have flowed in the past. Now today, the atmosphere is too thin and the temperature is too cold for water to stay in a liquid form for very long. It would either freeze or evaporate right away. But yet, we see thousands and thousands and thousands of dried up riverbeds all over the planet. So we know that sometime in the past, Mars had a lot of liquid flowing around on the surface, and maybe that time was the same time when life was emerging on our own planet. And so if we had lots of liquid in the first early history and life emerged from that, why couldn't the same have been true on Mars? So that's why we go to Mars. That's why we go exploring. And we go exploring with wonderful spacecraft like this one, my favorite. This is Curiosity. She's currently roaming the surface of Mars. She landed on Mars August 5th, 2012, which happens to be my birthday. It was awesome. Best birthday ever. It was great. I was on it. I've been on the Curiosity team since it started over a decade ago, and since we first conceived of the science that Curiosity is doing, and I was involved in a couple of the different scientific sensors that she's carrying, and I call her the girl because she's smart and good looking, so I figured she must be a girl. So here she is. So we've been there for about a year and a half. We've had our first scientific papers come out, and for scientists in the crowd, getting on the cover of Science magazine is like, woo! So that was a pretty exciting thing. I'll tell you just a bit. I don't have nearly enough time to tell you about all of the great things we're doing, but give you a couple of things. So what's Curiosity trying to do? She is trying to understand whether those ingredients were there on Mars. Did we have those different ingredients together? Could Mars have been a habitable environment? Now, is she going to find something alive? Well, probably not. That's a pretty tough call. But did we have all those ingredients there? Can we confirm that? So that's really what she's designed to do. Beautiful machine, the size of a Mini Cooper, nuclear powered. She's got plutonium in her tail there. Got incredible sensors, stereo, video cameras. She's got a laser beam on her forehead. She can blast the holes in the rocks. She can do all kinds of amazing stuff. And she's got, well, she basically can do what a geologist would do. If I was there on Mars, I'd be thrown up the whole way getting there, but if I was there, I would walk around and look for the most interesting rocks, so she can drive around and do that. I would approach the most interesting rock and pick it up and then try to figure out what kind of rock it is. She has the tools to do that. And if it was a really, really interesting rock, I'd put it in my backpack and I'd bring it back to Earth, to my lab, where I could analyze it in a ton of detail. She can't bring anything back to Earth, but she does have a fabulous lab right here in her belly that, where we can drill into rocks and scoop up soils and feed them right into these instruments. They're incredible quality, and we've done that. And we found water and soil. We found really interesting minerals that look like they formed in a lake environment. I'll tell you all that in a second. But so she's done an incredible thing. And then this is her selfie, by the way. So the other thing is that she has a robotic arm, and that arm has a camera on the end of it. And this is literally her taking a picture of herself on Mars. It's actually 55 pictures that we stitched together, but still. And just like you don't see your own arm in your own selfie, you don't see her arm in this picture. But in this picture, she just scooped into the soil here and fed that into the lab in her belly. So we're driving around on Mars, and we're eventually going to go drive up this beautiful mountain here called Mount Sharp, which I'll show you a picture of here in a second. But, so just to give you a little bit of a taste of what we're finding, we went to this particular place that we are on Mars because we thought that it might hold evidence that there was once a lake there, that there was once water flowing around. And indeed, that is what we have found. And you can see it just from looking at the rocks. So again, geologists, this is like candy dust. And look at all these rocks close up. But things like these different layers that go slightly different angles and directions tell us about water flowing around. see it very well, but there's some nice white splotchy things and different veins in these rocks where water was flowing through them. And here, is this thing that looks like a piece of jackhammered sidewalk. Actually is a rock that's made of lots of pebbles that have been stuck together. We find this kind of rock a lot on Earth. We find it in stream beds. So again, here, direct evidence, just from looking at the rocks, without even doing any fancy lab chemistry, that water was flowing around the floor of this crater that we're sitting in. It's absolutely a phenomenal thing. And in fact, we think, so here's this big mountain that will eventually drive up, and we're looking down on our crater. There's the rim of the crater. This whole thing is about 80 miles across. So we're sitting down here somewhere. We think this whole thing was once a lake. And you can see right here one of those wonderful dried up riverbeds I was telling you about. Probably is where the water flowed in, flowed downhill, and pooled up down here. That's what we're seeing. So we're just starting to see, so we found the evidence that there was liquid water sometime in the past. Stay tuned for evidence about those raw materials, the organic molecules that make up living things. We're still looking for those, but we're getting close, we think, we hope. And then energy sources, we've been looking at the rocks and see plenty of nice chemicals for anything living that they could have eaten. So if you were a bug living on Mars, say 3.5 billion years ago, you would have been perfectly happy swimming around in the lake because we think it was there. Very exciting findings from Curiosity so far. And in fact, I'm going to show you now, it's just such an extraordinary mission. And I want to show you some of my favorite images that we've taken over the last year and a half.
What is it?
Work on Curiosity Rover, so it's a phenomenal piece of equipment there on Mars, doing great science every day. So we think that we've got great evidence that there were habitable environments on Mars. Do we have the smoking gun? Did anything crawl by the rover yet? No, it hasn't. Did we analyze any, amino acids or DNA? No, we haven't done that yet. And this mission probably won't be able to do that. But for the future, we're feeling pretty optimistic about the fact that there were these environments on Mars where life could have gotten started. And now we need to go see whether we can find that evidence. And so that'll be for future missions to do. And speaking of the future, so let's think about what else is coming down the road for answering this amazing question, because there's so much more universe out there to explore. In fact, there's a lot more solar system to explore. There are other environments even in our own solar system that will be interesting for us to go see whether or not those conditions for life could have been right. These are the four moons of Jupiter, four of the, I think there's 67 at the moment, known moons of Jupiter. But these four are by far the largest. And this is in order out from Jupiter: Io, Europa, Ganymede, and Callisto. Beautiful, beautiful objects. Ganymede is larger than Mercury, the planet Mercury. So they're very, very significant sized moons. And you would think that being out as far as Jupiter, which is 5 times further from the sun than the Earth, that's too far away for there to be liquid water, say, if it's too cold. But it turns out that something interesting happens with these moons. And Europa in particular, which is the second moon out, actually in Io as well, it's kind of funny here. They're so close to Jupiter, and as they go around and around Jupiter, which is massive, they go around and around Jupiter in their orbits, they get sort of pushed and pulled by Jupiter's gravity between Jupiter and one of these outer moons, pushed and pulled and pushed and pulled and pushed and pulled. And that causes heating. Just like if you were to take a credit card or a wire hanger back and forth, and it gets warm. That kind of heating is the same thing that happens on these moons. So much so that Io has a dozen active volcanoes on it. They're erupting right now. It's so hot. And Europa, which is a little bit further out, so it doesn't get pushed and pulled quite as much, has an outer shell that is water ice, but we think beneath it, the warming is such that the ice is melted, and there could well be a liquid water ocean beneath that icy shell. Why do we think that? Well, when we look at the surface of this moon, and this is now a close-up picture of the surface of the moon, and see, when I first got this slide, I was working at a different university that my boss used to work at. This is a picture of the icy surface. Now, this is solid water ice. First of all, it's really cool looking, right? And all these different faults and things going across. But you can see here that it looks like there's almost like icebergs that have floated out in the sea, and then that sea froze. So this one right here, you can see is kind of tipped on its edge. This was a place where liquid water erupted onto the surface and broke up that ice and then froze it. Because right at the surface, it's very cold. But again, we think it's that liquid water from below that occasionally is able to peek up to the surface. So wouldn't it be amazing? Now, we still need to confirm this, but wouldn't it be amazing if we could send a little submarine to run around in that ocean on a moon of Jupiter? See if there's anything swimming around in there. That would be pretty interesting. And For now, our next missions to Europa really want to confirm the presence of this ocean, understand where we might be able to access it with a future mission that could drill down and drop in a little submarine. So that's one big possibility for the future. Another, of course, is to follow up our incredible robot explorers on Mars with people. That's another big thing that's in our future, is the ability to send humans to go explore the red planet. Now, we can talk about this more if you all want during Q&A, but in fact, what it takes the rover a day to do, a human can do in about 45 seconds. So it's far more efficient, not to mention the cognitive abilities of the human to very quickly see something and respond to it, to have human explorers that really answer this question about are we alone on Mars would be a fabulous thing to be able to send those humans in the future. And we're working towards being able to do that with the technology that we're working on now for things like radiation protection and long-term living off the planet and all sorts of challenges that we have to overcome because it's a lot further away than the moon. The astronauts went to the moon. It took them 3 days to get there. To get to Mars would take about 6 months. And you can't do an Apollo 13 style abort and come back. So it's quite a serious mission. But it is in the future. But now let's talk a little bit about what's even beyond our own system of planets. What's beyond the sun and our planets? What else might be out there? Let's go all Star Trek here for a minute, okay? When do we get to do that part? When do we get to go explore what's beyond Earth? As Hugh mentioned in the introduction, until maybe 15 years ago, we thought there must be planets around other stars. We just had no direct evidence that they actually existed. We knew the stars were there because we could see them in those galaxies. We could see the billions and billions of stars, right? But you can't see planets. Stars are really bright. Planets are really faint. They're hard to see. When you point a telescope, you see stars. You can't see planets. That's changed in the last 15 years. We have had now the ability to be able to detect planets around other stars. We can't take a picture of them yet. We can see them by the effect that they have on their parent stars in a couple of different ways. And this is a mission called Kepler telescope right here. That is doing this in space. It's discovered almost 2,000 planets around other stars. 2,000 planets. Over 1,000 solar systems. A lot of them have more than one planet in them. And here's how it does it. It stares at a piece of the sky. This is its field of view here. It looks at thousands and thousands of stars. There are stars in our galaxy, it turns out. And it watches them very closely to see if they get a little bit dimmer when a planet goes in front of them. So they're looking for eclipses, right? They're looking for a time when a planet goes in front of a star. It's very sensitive, so it can just see a little tiny wink of light go away, far less than 1% dimming. Kepler can see it. And using that, it has detected these thousands and thousands of planets around other stars. And just last week, did anybody hear this? They announced this big announcement about the first planet that looked to be about the size of Earth in an orbit about as far away from the star as Earth. So it's our first true Earth-like planet outside our solar system. That's amazing. Turns out this kind of technique is very sensitive to planets that are very close to their stars, so it's going to be really hot planets. Planets that are as far away as Earth or beyond are harder for them to see, because you can imagine it wouldn't actually go in front of the star very often. You have to get kind of lucky to see it. But still, thousands and thousands of other solar systems. So what we're going to wind up with here is we're going to show you 3 animations. And the first one shows all of these thousands of planets, every single thing that Kepler has discovered since it was launched a few years ago. And you're going to see them all on the screen. And I'll just give you a little primer here because it can be a little bit overwhelming. So you're going to see lots and lots of things moving around on the screen. In the very upper left is our solar system for scale. So you can see how big most of these solar systems are compared to ours. So in those you can see how close the planets are to the star and how big they are relative to the size of our planets. You see a lot of big planets really close to their stars. Very interesting and very strange. But then we've discovered thousands and thousands of planets. You can see all the planets that Kepler has discovered. Then they just released this wonderful animation of the planet that's most like Earth that they've discovered. Now don't be fooled, they're going to show you at the end of this a picture of a planet that looks a lot like Earth, and you're going to say, oh my God, it's an animation. You don't have a picture of the planet. We can't take a picture of the planet. We don't have that technology yet. So the very last animation shows you a telescope which would be capable of taking that picture. A telescope that has this beautiful flower-like structure that opens, that flies way in front of the telescope and blocks the light of the star so that you can see the planets, right? Just like you can block the sun so you can see better when you're driving into the sun. You've got to block that bright starlight so you can see the things around it. That's in the future. That's like our submarines on Europa, humans on Mars. That's something yet to come. So let's go watch some planets. So I would be happy to entertain questions. So before we do, please just take a moment and thank our amazing musicians.
In all, in that beautiful shot of those 1,779 solar systems, if you were looking down at each one of them from the top, the planets seem to be moving in a counterclockwise direction. Is that true in every one we found?
No, they probably made them all go the same direction for the purpose of the video. So it depends on which side you're looking at the system from, and we don't really know that. Right? You can make a decision about which way is north. In our solar system, all the planets go around the star in the same direction. In all of the systems that we have discovered, this is a good question, I believe the planets go around the star in the same direction. We would expect that if they formed as part of that rotating cloud of gas, that for the most part they really should go around the star in the same direction. But in any given solar system, their orientation could make it look like they're going the opposite way in one than the other, but that's just an orientation question. But they should, all planets in a single solar system should, yes, nature has surprised us before, but should go around the star.
Should go clockwise.
Why isn't that true?
We'll find out.
Yeah, so that's a great question. So is it too egocentric to think that that life needs those same things that we have? So on one hand, I could say yes. On another hand, what we're saying is it requires water, which is hydrogen and oxygen, two of the most abundant elements everywhere in the universe, and we do see them everywhere. They're very easy to make, hydrogen, Big Bang, and oxygen inside of stars. And water turns out as a liquid to have some special properties that help facilitate the chemistry of life. There are other liquids that people do think about, liquid hydrocarbons and things like on Titan, the moon of Saturn. But water, we think, does have some special properties that make it at least smart to start there. And then I think the other question we always get is carbon-based life. Does it have to be carbon-based life? And again, not necessarily, but carbon is very abundant in the universe. 3 helium atoms stuck together makes carbon, and so it makes very easily inside the stars we make a ton of carbon. So there's a lot of it, so that's good. 2 is it can very easily form long, complex molecules, and I think the complexity of molecules of living things is fairly extraordinary. So when you think about other chemicals that can make long, complex molecules like that, silicon maybe, but it's harder to imagine. Now, we might just not be being imaginative enough, and we certainly would accept that possibility. But certainly given the abundance of these different elements and their how good they are at doing the things that everything life does, it seems a reasonable place to start. It shouldn't be the place to finish, but it certainly seems to be a reasonable place to
So
start.
maybe our periodic table is not the same as theirs?
Well, so a periodic table is just our way of classifying the different kinds of fundamental particles and the numbers that they stick together. They probably don't call it carbon a carbon, but it's got 6 protons and 6 neutrons and electrons going around
Hopefully
it.
you'll be alive
So whatever
to
that
figure out
thing
the answer
is,
to the question.
so protons are protons, and all the chemical elements are made up of the same stuff. They're just made up of different numbers of them. So it seems reasonable that, again, when we can detect those elements out in the universe, and we see that they're the same everywhere. We see nature's really efficient at making all of them and populating that whole periodic table, which is kind of incredible. But you're not going to find a new chemical element between carbon and nitrogen because of the way chemical elements are made up. So we think we do have that structure down pretty well. But again, every time we think we really, really get it, the universe surprises us. So, yes.
So you realistically is time frame for getting humans on Mars? There's a mission underway in Holland.
Yes. So I was asking about the realistic timescale to send people to Mars. So the government is working on the technology technologies to do that. There are technologies we need, there's money we need, which is probably harder these days. And realistically, I think, NASA's goal is in the 2030s to at least do maybe not a landing, but a round trip. That's going to be pushing it, but I think it's possible. Doing landings later that decade is possible. There are now private entities, and this is very interesting. The realm of spaceflight is changing. New entrants, new companies, new entrepreneurs. Elon Musk, everybody's heard about Elon Musk is doing right with his rockets, and Triton and Richard Branson. That's right, and there's a company in the Netherlands who is called Mars One, which is proposing to send people on a one-way trip. I think we all know people we'd like to send. Thousands of people sign up or something. I mean, say they would go when the one-way trip worked. And they pay money. They pay money. That's a lot of the time. And so, there's interest there. I know those guys. They're not going to Mars. It's a great way though to get people talking about it, thinking about it, and think about it. If you're going to Mars to settle Mars, not as an astronaut expecting to come back, the government probably can't send people on one mission at least at first. But when people came to America, they didn't have any expectations of going back. When you're going to settle a new world, you think about it in terms of a one-way trip. That's still a little ways off though, for that's going to stay. Yes.
How sure are you that planets like Curiosity doesn't contaminate the atmosphere?
So good question. So how do we know if we were lucky enough to measure organic molecules with Curiosity that we didn't bring them with us, right? We are very careful about this. In fact, there's a whole person at NASA whose job it is to make sure that we do this well. She's called the Planetary Protection Officer, which I think is the coolest job I've done. So she is meant to protect Mars from us, to make sure that anytime we go there with a very clean spacecraft. And she's also meant to protect Earth from the Martians. So if we were to try and bring things back from Mars, they want to make sure that it's well contained, and even if we say that very low probability contains life, none of us want to be responsible for the Andromeda strain or anything like that. So she's just there to protect the planets. So we clean our spacecraft meticulously, especially if we have an organic detection experiment. That part, so the sampling part of Curiosity is meticulously cleaned. Even so, we do have some background in our instruments. So we actually do measure, we have measured organic molecules on Mars. We think a lot of them came from Earth. And so we do, and it's because we got some molecules. And so we always have to be extra careful to make sure that we properly use this method to eliminate all possibilities before we accept them. But it is absolutely something we worry about all the time. So should we wrap up because we need to let everybody get on to their next thing? I'm happy to stick around for a few more minutes though and take some more questions if folks want to come down. And Susie, do you want to say anything before we go? Thank you all so much.